All right, today we are diving into one of the most powerful and, honestly, beautiful ideas in all of science and engineering. It's like a special pair of glasses that lets us see the hidden structure of the world around us. Everything from the sound of a guitar to the data streaming to your phone right now. So, let's get into it. Let's start deconstructing reality.
Think about it for a second. On the surface, they seem completely different, right? One is something you can hear, another is an invisible signal flying through the air, and the last one is a picture on a screen. But deep down, they all share a fundamental secret. And figuring out that secret, well, it changed everything about modern technology.
And there it is. That's the big idea. Any complex signal, it doesn't matter how messy or random or chaotic it looks, can be perfectly built by just adding together a bunch of simple, smooth, predictable waves. It's like discovering that all of reality is just a kind of cosmic symphony.
To really get our heads around this, we're going to stick with this idea of a recipe. Think about a complex musical chord. When you hear it, it sounds like one rich sound. But we know it's really just a combination of individual notes being played together. Our goal here is to figure out exactly which notes are in any signal and how loud each one is.
And this is the tool we use, Furrier analysis. It's the mathematical process that lets us take any signal, any pattern at all, and find its secret recipe. It's basically the ultimate deconstruction kit. It doesn't actually change the signal, it just shows us what it was made of the whole time.
Okay, let's make this even simpler. Forget waves for a second. Imagine you've got a smoothie. You can taste it, you can see its color, but you have no idea what the exact recipe is. Furrier analysis is like a magic machine that can taste that smoothie and then print out a perfect list. 50% strawberry, 30% banana, 20% yogurt. It gives you the ingredients and their amounts.
Okay, so let's grab our first tool from the Furrier toolbox. This one's called the Furrier series, and it has a very specific job. It's designed for signals that repeat themselves over and over in a predictable cycle. Like the steady hum from your air conditioner or a single sustained note from a cello.
Now, whoa, don't let the math scare you off. Seriously. All this equation is saying is that our signal, which we call x of t, is simply the sum of all its ingredients. For each ingredient, that dn part tells us the amount of it, and the e part is the ingredient itself, a pure, simple wave. We just add them all up and we get our original signal right back. That's it. It's just the recipe. So, the big question is, how do we find those amounts? How do we figure out the d sub n values? Well, we use this thing. This is our magic smoothie analyzer. We pour our complex signal, x of t, into this process, and the math figures out the exact amount of each simple wave that's hiding inside. It is, quite literally, the recipe finder. And this leads us to a really crucial idea. We now have two completely different ways of looking at the exact same thing. In what we call the time domain, we see the signal how we'd normally see it, as one complex, wiggly line moving through time. But in the frequency domain, we see its recipe, a simple, clean list of the pure frequencies that build it.
And boom, this is what that recipe actually looks like. We call it an amplitude spectrum. Each one of those bars is one of our simple wave ingredients. And the height of the bar, that tells us how much of that specific frequency is in our signal. It's our smoothie recipe, but for waves.
Okay, that's all great for things that repeat, but let's be real. A lot of things in life only happen once. A single clap, a flash of lightning, a word that you speak. These signals aren't periodic. So for these, we need a more powerful tool. And this is where the Furrier transform comes into the picture.
Right. The Furrier series, with its neat, separate bars of frequency, it kind of hits a wall here. A one-time event is kind of like a repeating signal where the time it takes to repeat is infinite. So what happens to our nice, clean recipe when the pattern just never comes back?
This is where it gets really, really cool. As that time to repeat gets longer and longer, those separate bars on our frequency chart get closer and closer, and then even closer together, until, for a signal that never repeats, they all merge into one smooth, continuous curve. And this right here is the tool that finds that continuous recipe. This is the Furrier transform. You can see it looks a lot like our recipe finder from before, but this one is built to handle any signal you can throw at it, repeating or not. It gives us a value for every single possible frequency, not just a few specific ones. So let's look at a classic example. On the left, in the time domain, we have this simple little burst of energy. Imagine just flipping a switch on for 1 second and then off again. That's it. But on the right, in the frequency domain, we see its recipe, this beautiful, continuous wave that kind of ripples outwards. That's a very famous shape in math called a sinc function.
All right, now for something really wild. Let's talk about the impulse function. It's a bit of a theoretical idea, but it's for a signal that lasts for 0 time, but it's infinitely strong. It's like all of its energy gets delivered in one single, perfect, infinitesimally small instant.
So what on earth is the frequency recipe for an infinitely short spike? You'd probably expect something equally bizarre, right? But what the Fourier transform shows us is just astounding. The frequency spectrum is a flat line, just a constant value of 1 stretching across all frequencies.
I mean, just let that sink in for a minute. What this math is telling us is that a single, perfect, instantaneous crack in time is actually made up of an equal amount of every single frequency that exists, from 0 all the way to infinity. It's unbelievable.
So, okay, this is all fascinating, kind of mind-bending stuff, but why does it matter? Well, this ability to see the frequency domain, it gives us incredible powers. It gives us superpowers to manipulate signals in the real world.
The Fourier transform has all these amazing properties that engineers use every single day. Things that are super complicated in the time domain, like convolution, become simple multiplication in the frequency domain. It's incredible. But today, we're just going to zero in on one of these superpowers: frequency shifting.
Here's how the magic works. Step 1, you start with your signal. Let's say it's your voice, and it has its own frequency recipe. Step 2, in the time domain, you just multiply your voice signal by a really high frequency wave, like a pure cosine wave. And then, step 3, this is the magic part. In the frequency domain, your voice's entire recipe gets perfectly copied and just shifted way up to that new high frequency. And this isn't just some abstract math trick. This is literally how AM radio works. Your favorite station takes the music, which is a low-frequency signal, and uses this exact property to shift it up to its assigned broadcast frequency, like 101.1 megahertz. Your radio at home then just tunes in and shifts it back down so you can hear it. It's all because of this one superpower.
So at the end of the day, that's the ultimate power of Fourier analysis. It gives us a second, powerful perspective. By switching over to the frequency domain, we can easily see all the ingredients of a signal. And that lets us do amazing things, like filter out noise, compress images and audio into JPEGs and MP3s, and send information all around the world.
And that leaves us with one last thought to chew on. This whole idea, deconstructing complexity into its simple, repeating parts. It's such a powerful way to think. Sure, it applies to sound and light, but what about other complex patterns? The cycles of the economy, traffic flow in a city, maybe even your own daily habits. What could you understand better if you started looking for